Hello everyone, welcome to the presentation of our paper titled On the Design of Pattern Reconfigurable Alford Loop Antennas. My name is MD Abu Saleh Tajin. I am a PhD candidate at Drexel University. I work for Drexel Wireless Systems Laboratory under the supervision of Dr. Kapil R. Dandekar, who is the co-author of this paper. At the beginning of this presentation, I will show the motivation behind this work, and then I will briefly discuss reconfigurable antennas and the main point of discussion of this paper, pattern reconfigurable Alford loop antennas at 3.5 GHz. Then I will show the design and simulation of the Alford loop antenna at 3.5 GHz, and I will also show the fabrication and measurement steps, and I will show the results and discussion, and I will conclude the work with summary and future work. Reconfigurable Alford loop antennas, also known as the RALAs, have been used in many applications, including multiple input and multiple output or MIMO radio links, interference alignment, direction of arrival estimation, etc. Now, with the introduction of 5G, new radio bands are being available for use. RALAs can play crucial roles in those wireless systems. In this paper, we present a general framework and strategy for designing reconfigurable Alford loop antennas at the sub-6 GHz band. Antennas capable of modifying their frequency, radiation pattern, or polarization in response to overlying link or network needs are known as reconfigurable antennas. Reconfigurable antennas are an important part of the modern wireless systems. The dynamic nature of reconfigurable antennas allows for efficient use of the channel resources. Reconfigurable antennas are broadly divided in three categories: frequency reconfigurable, pattern reconfigurable, and polarization reconfigurable antennas. There are some versions of the reconfigurable antennas that apply some combination of these three features. RALA is a group of pattern reconfigurable antennas in the sub-6 GHz band. It was developed at Drexel Wireless Systems Lab. This is a dual-layer printed circuit board antenna consisting of 4 symmetric elements. It has 8 directional and 1 omnidirectional radiation beams. It has 3 operational modes: single arm, dual arms, and omnidirectional. The beams are switched using electronic switching. In this figure, we can see the top and bottom view of the Alford loop antenna. And as you can see, there are 4 symmetric antenna elements on the top layer and 4 symmetric antenna elements on the bottom layer. So the top and bottom layer elements, they make 4 symmetric dipole elements. And there are 4 parasitic conductors on the top layer. And this antenna is fed with a probe type SMA connector, and the outer conductor of the SMA is connected with the top layer of this antenna, and the central conductor of the SMA connector is connected to the small circle on the bottom layer. And the control circuits for switching the antenna beams are mounted on the top and bottom layers of this antenna. The Alford loop antenna is designed with an FR4 substrate. FR4s are cheap and easy to handle with milling machines. So the antenna design starts with the wavelength calculation at our frequency of interest, in this case 3.5 GHz, and we vary the D and R1 parameters so that we have an initially optimum performance of our antenna. And this is the list of the initial parameters when we started the design. Figure 2 shows the S11 or reflection coefficient versus frequency plot for different values of D. And as you can see that at 3.5 GHz, the best S11 performance is achieved for D is equal to 13.5 millimeters. So we stick with this value and we change the radius of the top layer or the R1 parameter from 6 millimeters to 15 millimeter. And as we can see here, the best performance is achieved for R1 is equal to 9 millimeters. While the D parameter helps us control the resonant frequency and operational bandwidth of this antenna, the L parameter gives us control over the radiation pattern and maximum gain of this antenna. As we vary the L parameter from 18.6 millimeters to 26.6 millimeters at a step of 2 millimeters, the 2D radiation pattern is plotted in this figure. And as you can see, the gain is maximum when L is equal to 20.6 millimeters, and it's slightly lower for 22.6 millimeters. But at 22.6 millimeters, the front to back ratio is better, and the side lobes are much more suppressed compared to this 20.6 millimeter version. So that's why we select L is equal to 22.6 millimeters. As we mentioned earlier, this antenna has three operational modes. In the single mode, only one antenna element is turned on, and the antenna radiates towards that direction. In the dual mode, two adjacent antenna elements are turned on, and the resultant radiation goes towards their common diagon. And in the omnidirectional mode, all the antenna elements are turned on, and this reconfigurable antenna behaves as an omnidirectional radiator. So the antenna was initially designed in the single mode. That's what we can see in this Smith plot. At 3.5 GHz, the antenna is impedance matched in the single mode, but the dual and omni mode points at 3.5 GHz are much more inductive compared to the single mode. So it's difficult to attain tri-mode tuning. So what we do is try to tune this antenna in the middle state, that is the dual state, so that the antenna works better at the dual state, and the other two modes are close to impedance matching. This is a fabricated sample of the proposed reconfigurable Alford loop antenna on FR4 substrate, and this is the top view and this is the bottom view. And here in figure C and D, we can see the close-up view of the control circuit at the top layer and at the bottom layer. The control circuit consists of pin diodes, inductors, resistors, LEDs, and jumper wires. So this is the point for positive control voltage, and this is the LED indicating which antenna elements are turned on, the resistor limiting the amount of current in the control circuit, RF choke inductor blocking the RF from entering into the control circuit, and this is the pin diode controlling the RF current flow into the antenna elements via the transmission line. The S11 or reflection coefficient of these antennas are measured with the network analyzer, and the radiation patterns are measured with EM scan. This is the experimental setup for measuring the radiation pattern of the Rala antenna using the EM scan board. And this is a complete Rala antenna with 6 jumper wires, and four of them carry the positive control voltage up around 3 volt, and 2 of them are ground conductors. And this is the coaxial cable carrying the RF signal to the antenna, and that is connected to the top layer of the antenna with an SMA connector. And the central pin of the SMA connector goes all the way to the bottom layer. This figure shows the measured S11 versus frequency plot. As we can see here, the dual mode is the best performer here with a very wide bandwidth, and the single mode is in second place, and the omni mode is in third place. So the overall common -6 dB bandwidth of this antenna is it ranges from 3.24 GHz to 3.78 GHz. The G parameter is changed from 0.5 mm to 1 mm to have the dual mode at the center of the Smith chart. Tri-state impedance match can be improved by adding a reconfigurable tuning stub at the antenna feed. This is the measured radiation pattern of the reconfigurable Alford loop antenna in the single states, and in the dual states, and in the omni state. To summarize our work, a general procedure for reconfigurable Alford loop antenna design is presented. At higher frequencies, the antenna elements become smaller, and as a result, there is less space for control elements. The integration and control becomes difficult. Control elements act as parasitic RF components. These are the main challenges of designing Alford loop antennas at higher than 6 GHz. In the future, adaptive impedance matching technique will be presented. This research is supported by the National Science Foundation. And here is the list of references we have used in this presentation. We would like to thank you for your patience. I would be glad to address or answer any questions you might have about this presentation or our paper.